Mr. Ainsworth here, starting you off with Chapter 9, which looks at testing a claim. And in this lesson, we're looking at the basics of significance tests. And keep in mind, the word basics here does not mean the simple stuff. It means the foundation of significance tests. And we're going to focus on just the first two objectives in this video. And the first objective is stating the hypotheses. Notice that is plural. There's going to be two. For a significance test about a population mean or population proportion, which means our claims are going to be based off of parameters. The second objective is interpreting a p-value in context. So we need to define a p-value and look at how it is used in relationship to significance. Before we begin, we need to look at confidence intervals, where we were to where we're going, which is significance tests, because those are the two most common ways to perform statistical inference. The main goal for confidence intervals was to estimate an unknown population proportion. In other words, we didn't know mu or we didn't know p, and we took a sample, we created an interval, and we tried to capture that unknown parameter. The reason why that's important is because it's a different goal for significance tests. Its goal is to assess the evidence provided by data about some claim concerning a population. So it's a formal procedure for comparing observed data with a claim whose truth we want to assess. And that claim is called a hypothesis. So there's some claim about a parameter that we're collecting data that we want to assess. And that claim could be about mu, could be about p. And we're going to express the results of the significance test in terms of a probability that measures how well the data we collect and the claim agree with each other. That probability, maybe that relates to p-value. So here's how I like to think of it. There is a claim about a population. We call that the null hypothesis. We observe something that makes us question that claim. And so we create an alternative hypothesis. And we're going to perform a test whose results are going to be expressed as a probability, a p-value, that will measure how well the data we observe and the claim agree with each other. So right here, this is the main thing we're going to be doing with significance tests. This is the basic principles behind significance tests. Let's break it down even simpler. Have you ever heard any of these claims before? 3 out of 4 dentists recommend the battery will last at least for 23 hours. There are at least 100 pepperonis on this pizza. Let's focus on that pizza one. What if there's 95? What if there's 98? What if there's only 80? If it's not exactly these numbers, if it's not exactly at 100 pepperonis, how far away must the data be before you start doubting the claim? And that's what we're going to be looking at with significance tests. So in other words, the goal is to assess the evidence provided by the data that we collect about some claim concerning a population. Let's use this example to help us out. Suppose a basketball player claims to be an 80% free throw shooter. To test this claim, we have him attempt 50 free throws. He makes 32 of them. So his p-hat, the sample proportion, is 32 out of 50, which is 0.64. So what can we conclude about the claim that he's 80% free throw accurate based on the sample, which we saw was only 64% free throw accurate? To help us with this, we're going to use the simulation which is below that dot plot, which represents 400 sets of 50 free throws, assuming he really is an 80% free throw shooter. So take a look at this. Each one of these dots is a p-hat of 50 shots. He says that he is an 80% free throw accurate shooter, so he should be around this area. However, what we observed is way out here at 0.64. And if I'm shocked by 0.64, I'm also going to be shocked by the 2 0.62s there. So I observed something way, way, way off in the tail. And the reason why that's important is because you can say how strong the evidence against the player's claim is by giving the probability that he would make as few as 32 out of 50 free throws if he really is 80% accurate in the long run. So, in other words, you can say how strong the evidence against the player's claim is by giving the probability that you would observe what you saw if his claim really was true. So our observed statistic here is so unlikely. It's in that tail. It's got a small chance of occurring if the actual parameter p equals 0.80 was true, that it gives evidence against his claim. It gives evidence that his claim is not true. And I want you to think of it just in this distribution. He should be here, correct? He says he's 80%. He should be somewhere in this area right here. But we observed him way out here in the tail. That is such a small chance of us actually observing that happen that it gives evidence against his claim. So his claim was that he was an 80% free throw shooter. And what we observed was that he was less than 80%. So if the claim is true, then the probability of us observing as few of 32 out of 50 free throw shots being made was 3 out of 400, 0.0075, less than 1%. It is so unlikely that we observed that it gives strong evidence against his claim. So based on this evidence, we might conclude the player's claim is incorrect. Now in reality, there's two possible explanations for the fact that we observed a 64% accurate free throw shooting. And the first is that, hey, his claim is correct, and by bad luck, a very unlikely outcome occurred. The second one is the population proportion is actually less than 0.8, so the sample result is not an unlikely outcome. Now what that means is the basic idea is this. An outcome that would rarely occur if the claim was true gives evidence that the claim is not true. So in other words, if he should be in this area, if the claim is true, and yet we observed him way out in this area, the fact that we observed this gives evidence that his claim is not true. I'm not going to go through an entire significance test here because that's what the next two sections are over. But I do want to point out the steps for significance tests. You're going to do state, plan, do, conclude. Now notice state, there's going to be null and alternative hypotheses in words and symbols. We'll address that. Plan, you have to name the inference procedure. Just like you had to name it for confidence intervals, you have to name it for significance tests as well. And you need to verify conditions are met. I wonder what those conditions are. Could they be related to what we did with confidence intervals? Now in the do part, if the conditions are met, you're going to sketch a graph. I wonder what type of distribution we're going to sketch. You're going to calculate a test statistic. That sounds familiar. And find the p-value of that test statistic. And then you're going to interpret the results in context based off of that. So keep an idea on this down and write it down if you need to later on. But this is really the steps for a significance test. The significance test starts with a careful statement of the claims you want to compare. Now the first claim is called the null hypothesis. It's usually a statement of no difference. The claim we hope or we suspect to be true instead of the null is called the alternative hypothesis. Now H sub O is the null hypothesis, H sub A is the alternative hypothesis. Now the test is designed to assess the strength of evidence against the null. So in this example that we have with the free throw shooter, this represents our hypotheses. H sub O, the null, is that he was an 80% free throw shooter. P equals 0.80. H sub A was that we observed less than that. P less than 0.80. And we also have to define what is P in context. It's the long run proportion of free throws made. So this is an example, by the way, of the state step here. We are looking at stating our null hypothesis and our alternative hypothesis. And notice null has no difference there. It's equal to what he claimed, 0.80. And the alternative is what we suspected or we thought we would see, which is less than 0.80. Here's some notes that I have. You can go ahead and read them. But what I want you to realize is the warning. The hypotheses should be expressed before we see the data. And think about it, you can't test the claim after you collect the data and observe something. You make your hypotheses before you collect the data. Never look at the data first and then create the hypotheses. Don't be that student. So when we're dealing with the hypotheses, the null hypothesis always has the form H sub O, the parameter equals the value, the claim. The alternative hypothesis has one of three forms: the parameter less than the claim, the parameter greater than the claim, or the parameter not equal to the claim. Now you have three spots down there that you're going to draw some distributions for. And we're going to kind of write them in and look at what the different tails of these hypotheses looks like. So to determine the correct form of your alternative, you need to read the problem carefully. Now, there are one-sided alternative hypotheses, which are your less than or your greater than, because that is going to be one-sided, either in the tail on the right side or the tail on the left side. What that means is the parameter is either larger than the null hypothesis, or it states inside the parameter is less than the null hypothesis. If it is two-sided, all we care about is that there is a difference, and we don't care which tail it's in. We don't care if it's either larger, we don't care if it's either smaller. So that has two tails in it. So again, we're going to keep these areas, and I want you to sketch a normal distribution. Don't shade them in yet, and we'll look at what that is when we go through. So hypothesis always refers to a population, never a sample. Do not write hypotheses with p hat and or with x bar. Don't do that. I mean, those are quick ones to eliminate on a multiple choice test. Be sure to state your alternative and your null hypothesis with population parameters, p or mu, never x bar or p hat. So now let's take a look at these three spots: the parameter less than the value, the parameter greater than the value, and the parameter not equal to the value for your alternative hypotheses, and we're going to use these situations here. So though it's on blue here, you're going to fill it in right up here. We're going to use these three distributions based off of cell phone battery life, college tuition, and car tire pressure. Now the three types of alternative hypotheses we can have is a one-sided less than, where your parameter is less than the value, a one-sided greater than, where your parameter is greater than the value, or a two-sided not equal to, where your parameter is not equal to the value. And we're going to look at these based off of these scenarios. So imagine a cell phone company. Mu is the number of hours of cell phone battery life. This cell phone company claims their battery lasts for 15 hours. So their claim, their null hypothesis, is mu equals 15. Now, we would not like buying that cell phone and having an average lifespan of our battery to be less than 15 hours. So that is why this one is a left-tailed distribution. So the distribution is based off of their claim being true, which means in the middle of this claim is their mu equals 15. And what's going to happen is we are going to create an area over here that we're going to call the rejection zone. And over here, if we observe something way out in this shaded area, this left-sided tail, I mean, it would be so rare for that to occur. We're going to call that, the rejection zone. We're going to reject the null. But if we observe something in the other zone, we're going to call this the fail to reject the null. And I want you to realize, even way over here, we're not rejecting the null. We're still fail rejected, because if they tell me the battery life of my cell phone is 15 hours and I get 60 hours out of it, awesome. I'm not going to be upset. So that's why this one's left-tailed, is we only care if our battery is less than 15 hours. If it's over 15 hours, that's a victory. We're cool with that. So notice, and I would have labeled there where your fail to reject zone is and where your rejection zone is. Now, if we look at this one's college tuition, the average cost of college tuition. So mu is the average cost of college tuition. And if we look at this, let's say the college tuition, I know, right, is the null hypothesis is $7,000. We would be concerned if we said, sweet, I have $7,000 that I'm going to pay for my college tuition. Great. And all of a sudden we get there and they go, whoops, really it's $15,000. So the alternative is we don't want more than $7,000 because they told us $7,000. Now, if they told us less than, awesome, more money for me. But in this case, what we're going to look at is they're telling us right here, hey, their mu is 7K, 7,000. So we're going to look at the tail on the right-hand side because we don't want to pay way more than 7,000. So this is going to be our rejection zone. So this is where we reject the null. And on the left side, this is where we fail to reject the null. Because we don't care if the tuition's 3,000. That's good news for us. We only care if it's way over 7,000 in that rejection tail. Now, in this case, it's a two-sided significance test for us. And this one deals with tire pressure. And so if mu is the tire pressure in PSI, and the null hypothesis is you open the door, you look at the tire, you look on the wheel, and you go, yep, it says 32 PSI. That should be the average. Well, for your tire, it matters, by the way, if your tire is overfilled, because it could pop, or underfilled, because you would warp the tire. You would ruin the tire. So in this case, it's a two-sided significance test. We would have an alternative hypothesis where we care if it's both greater than and it could also be less than for it. So we care if it's in either of the tails. We don't care which one, we just don't want it to be there. So in this case, their claim is, hey, you need 32 PSI, so that should be in the center. So we care if we are underfilled. So anything in this tail is going to be the rejection area. You're going to reject the null. Anything in this tail is overfilled. And again, that is going to be reject the null. The center area is our fail to reject. So this is why we say be careful reading, is because sometimes you care if it's less than. You don't want cell phone battery lives to be less than what they say. You don't want college tuition to be greater than what they say. And when you have a car and you have the tires, they can be overfilled or underfilled. And so you need both. So be careful reading on determining whether the alternative is less than or greater than, which are your one-sided significance tests, or not equal to, which are your two-sided. And so here's kind of my notes on it as well, which you can see I kind of outlined before. A little bit of help is right here. For one-sided, when a direction to the relationship is expressed, you're probably dealing with a one-sided test. Keywords to look for: less than, lower, smaller, less, etc. Greater than, higher, bigger, more. So those are keywords that lead to one-sided alternative hypotheses. Two-sided alternative hypotheses is when a direction to the relationship is not expressed. It just states that they are different. So some keywords or phrases are: has the value changed? Is there convincing evidence that the true value is different? We don't care which side, just that it's different. Or even test the claim that the parameter equals the value. So no direction is given. So these are in your notes, but these are really important keywords and phrases to look for to determine whether or not your alternative should be one-sided, less than or greater than, or two-sided, not equal to. Let's use this job satisfaction study to help us out. Does the job satisfaction of assembly line workers differ when the work is machine-paced rather than self-paced? So right away, I'm thinking, it just says, is it different? It doesn't tell me if it's greater or is it less. It just says, is it different? So I'm leaning towards a specific type of alternative hypothesis right now. Are you? So one study chose 18 subjects at random from a company with over 200 workers who do electronic assemblies for devices. Half of the workers are assigned at random to each of the two groups. So both groups do similar assembly work, but one group is allowed to pace themselves while another group works on a assembly line that moves at a fixed pace. After 2 weeks, they take a job satisfaction survey, and then they switch work setups. And they take the test again for 2 more weeks. So the response variable after they do this is the difference in job satisfaction scores, self-paced minus machine-paced. So what I want you to realize is this is similar to your AP free response group problem. Is you're looking at the difference of their job satisfaction scores, and it's specifying the way you subtract them. So I would personally underline this part right here because this is a really important thing in the future that we're going to use. So it says describe the parameter of interest. So this is always important when it comes to context. So in this case, our parameter of interest is mu sub d, which is the difference, self-paced minus machine-paced. So yeah, we wrote down mu sub d, but you always have to state what order the subtraction is occurring in job satisfaction scores and the population of all the assembly line workers in the company. So part B says, okay, now state both hypotheses, the null and the alternative. And so the initial question asked whether it differs. It didn't say, hey, is their score less than on average or is it greater than average? It just says, is it different? So what we're going to do is our null is going to be, hey, there is no difference. The mean scores are the same. There is no difference between job satisfaction versus self-paced versus assembly line. The alternative is, hey, there is a difference. We don't care which direction. We just think that it is different. And so mu sub d is not equal to 0. So we have our null hypothesis, mu sub d equals 0. We have alternative hypothesis, mu sub d is not equal to 0. So the data that we collected said x bar was 17. So we're just making up the data right now says x bar was 17. S of x equals 60. Now that means the workers rated the self-paced environment on average 17 points higher than the fixed machine assembly line. Now researchers performed a significance test and they found a p-value of 0.2302. Alright, so explain what it means for the null hypothesis to be true in this setting. And so in this setting, if your null hypothesis mu sub d equals 0, that means the mean difference in satisfaction scores self-paced minus machine-paced for the entire population of assembly line workers is 0. And that means if the null is true, that workers do not favor one work environment over another. That's what your null hypothesis means. There is no difference. D means difference. There is no difference in how they favor the work environment. The workers don't favor one environment over another. Now, what if I were to ask you about the p-value here? About the p-value of 0.2302. Is that rare? By the way, what percent do you think is rare? And we always kind of use that 5% as the, wow, that's rare that occurred. It's unlikely. So 0.05, wow, I got 0.2302. Is that rare then? And so when we're dealing with a two-sided, do keep in mind that we're dealing with this one, that there is no difference. So somehow that p-value has to help us determine which region we are in. You reject the null, or you fail to reject the null. So somehow we're going to use that p-value to help us out. Again, it wasn't one of the questions here, but oh, if we go to the next slide, it deals with interpreting p-values. Who knew? So the null hypothesis states the claim that we are seeking evidence against. And the probability that measures the strength of the evidence against the null hypothesis is called a p-value. The probability value for the strength of the evidence against a null hypothesis. So the probability computed assuming the null is true, that the statistic would take a value as extreme, that location, or more extreme towards the tail than the one actually observed is the p-value of the test. The smaller the p-value, the stronger the evidence against the null hypothesis. Well, wait a second. Let's go back up to this. So the smaller the probability we get, wouldn't that mean we are in these small areas in the tail? So we would reject the null hypothesis. The larger the probability, wouldn't you fall in regions closer to this area? So that would mean we fail to reject it. So we're still going to be looking at distributions and the shading of them. And that's kind of what that's trying to help you with. So small p-values give evidence against the null hypothesis. And they say the observed result is unlikely to occur if the null is true. So small p-values, small probabilities are going to be located in the tail, and it gives evidence against the null hypothesis. It says it's unlikely to occur if it was true. Large p-values do not give evidence against the null hypothesis because they say the observed result is likely to occur by chance when the null is true. Be mindful of the phrasing in that last slide. We can think of the phrasing as something that's really important, how you draw your conclusions. And we can use this idea of a jury to help us. So when a jury reaches a decision, do they either say we find the defendant guilty or not guilty? Why don't they say innocent? Is someone being found not guilty the same as saying, hey, they're completely innocent? Or could they have committed the crime and gotten away with it? So when we're making our conclusions, it's really important for us to be mindful of how we state them. And that's crucial with how we write in this chapter. Maybe the juries don't make sense. So let's make it something that does relate to you. If you ask someone to prom, you say, hey, will you go with me to prom? Here are some responses. Absolutely, you're the love of my life. No way, jerk. Or, I'm not saying no. Is not saying no the same as saying yes? So if you ask someone to prom and they say, I'm not saying no, does that mean they're really going to prom with you? These are things for us to keep in mind with how we draw our conclusions or how we phrase our conclusions based off the p-values with our significance tests. Oh, look at that. There is a part D in this job satisfaction one. It is interpreting the p-value in context. So the p-value is the probability of observing a sample result as extreme or more extreme in the direction specified by the alternative hypothesis when the null is actually true. So the p-value is the probability of observing a sample result as extreme or more extreme in the direction specified by our alternative hypothesis when what the claim was, the null hypothesis, was true. And I honestly, you're going to be asked many times to interpret the p-value. So you should really underline some of the key words there. Maybe write it in your notes part of your formula sheet. Now, because this alternative hypothesis is two-sided, the p-value is the probability of getting x bar as far from 0 in either direction as the observed x bar, which was 17, when the null was true. That is, an average difference of 17 or more points between the two work environments would happen 23% of the time by chance in the random samples of 18 assembly line workers when the true population mean, mu sub d, was 0. So let's think about it this way. An outcome that would occur so often just by chance, almost 1 in every 4 random samples of 18 workers, when the null is true, is not convincing evidence against the null. We fail to reject the null hypothesis. And I want you to look at how that is said. We fail to reject the null hypothesis. We do not accept the null. Don't be that student who accepts the null. You never accept the null. You fail to reject it. You do not have evidence that allows you to reject the claim, so you fail to reject the claim. No one likes to admit when they're wrong. So you're not going to say, I accept the fact that the null was true. Never accept the null. What you do is, you don't admit you're wrong. I fail to reject the null. That's the key to significance tests. So again, look at the interpretation of the p-value. It is the probability of observing a sample as extreme or more extreme in the direction specified by the alternative hypothesis if the null was actually true. So the next part there really is an in-context way of interpreting the p-value. All right, so our final step in performing a significance test is drawing a conclusion about the competing claims that we're testing, the null and the alternative. We're going to make one of two decisions based on the strength of the evidence against the null hypothesis and in favor of the alternative. We either reject the null or we fail to reject the null. So if our sample result is too unlikely to have happened by chance, assuming the null is true, we reject the null. Otherwise, we fail to reject the null. So, fail to reject the null decision, it does not mean the null is true. And again, notice that. If you fail to reject, it does not mean the null is true. It only means that you do not have enough evidence to prove it wrong. You should never accept the null. You should never use language that implies the null is true. So in a nutshell, if the p-value is small, that means you're in the tails. So it should not have occurred because it's a small chance, so you reject the null. And what you do is you conclude the alternative in context. If the p-value is large, it's in the bigger part of the distribution, so you fail to reject the null, and you cannot conclude the alternative in context. So in other words, how do you make your final statement if you fail to reject the null? There is not enough evidence to conclude the alternative in context. That's it. You don't admit you're wrong. You don't admit the null is true. You just say, I don't have enough evidence to conclude what I wanted to conclude. Well, how do you know if the p-value is too small? What's the rule that we use for it? Now, there is no real rule for how small a p-value should be to require rejecting the null hypothesis. It's a matter of judgment in some situations. But we can compare the p-value with a fixed value that we regard as being decisive, allows us to make a decision, and that is called the significance level. And what we do is we use the Greek letter alpha to represent that significance level. When our p-value is less than the alpha that we choose, we say the result is statistically significant. So we can do statistically significant stuff now. So if the p-value is smaller than alpha, we say that the data are statistically significant at that alpha level. We have to specify that level. In that case, when that happens, we can reject the null hypothesis and conclude that there is evidence in favor of the alternative. So if the p-value is less than the alpha, we can reject the null and conclude the alternative. When our p-value is greater than or equal to the alpha, we fail to reject the null and we cannot conclude the alternative both in context. Now, what's a good alpha level? I wonder if that 0.05 that we've used before, that magical 5, if that's a good alpha level to use. Now, if they don't specify the alpha level in the problem, you use 0.05. So here's some notes for me. One does not accept a null hypothesis. You must fail to reject the null hypothesis. So never accept the null. Don't even apply it. If the p-value is less than your alpha, and I'm just showing you an example here, 0.05, you reject the null and you conclude the alternative in context. If the p-value is greater than or equal to the alpha, you fail to reject the null, and you do not have enough evidence to conclude the alternative in context. So after you make the decision, you must insert appropriate context and interpretation in there. So here's some more of my notes when it comes to significance levels. Some scenarios is your alpha level of 0.05. What that means is you are set an alpha level that requires that the data give evidence against the null hypothesis so strong that it would happen less than 5% of the time just by chance if the null was true. Your alpha level for scenario 2, let's say it's 0.01. That's requiring the data give evidence against the null hypothesis so strong that it would happen less than 1% of the time just by chance when the null is true. With this low of a p-value, we're looking for stronger evidence against the null hypothesis. So if a p-value is less than alpha, the data is statistically significant at that alpha level. When this happens, we reject the null hypothesis and conclude there is convincing evidence against the null and in favor of the alternative. Now, the whole idea of statistically significant does not mean important. It means not likely to happen by chance. So, statistically significant does not mean important. It means not likely to occur by chance. So, a company has developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. I see direction there, by the way. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Say, it costs more to produce them, so we better make sure they last longer. So based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use. on average. The company selects a simple random sample, random, of 15 new batteries and uses them continuously until they are completely drained. A significance test is performed using these two hypotheses. So I want you to realize how they came up with these hypotheses. The claim that they're used to from observed data from before is that their batteries last on average of 30 hours. So the null hypothesis is mu equals 30 hours. Now, they want to make sure these batteries last more than 30 hours because they cost more to produce. So they want to make sure they are lasting longer. So their alternative is one-sided. They have mu greater than 30 hours. And notice they are defining mu. And you know it. You know I'm going to say it. If you don't define it, you don't get to use it. So when they do this, their resultant p-value is 0.0276. Well, hold on a second. Let's draw a normal distribution here. All right, so I have my normal distribution, and they're saying, hey, right here, you know, that's where they're saying their mu equals 30. They want to observe, you know, hey, we want to make sure it's greater than 30. So what they found is they found a p-value of 0.0276. So way somewhere out there. That's what they observed, and they need to figure out what that means. So if they got a p-value that extreme, what does that mean? So what conclusion can they make at an alpha level of 0.05? So if their p-value is 0.0276, that's the area under the curve, the probability under the curve. You should understand that from normal distributions, from our table A, our z-scores. The alpha level says, hey, 0.05 is the area over here. So this is alpha level 0.05. If it falls in that area, we are going to reject the null. So anything less than that 0.05, we're probably going to reject the null. Anything that is greater than 0.05, I mean, that would be area way over here. So what does this mean? Since the p-value of 0.0276 is less than our alpha level for our sample, we can say the result is statistically significant because we have sufficient evidence to reject the null hypothesis. In other words, we can conclude the deluxe AAA batteries made by this company last longer than 30 hours. It was so unlikely for us to see a 0.0276 probability way out here in the tail by chance, if the null was true, that we can reject the null and conclude the alternative. So if it fell in that tail, we rejected the null. So maybe I need to do a better job with that alpha level 0.05. That is the area under the curve of a normal distribution. So that sets your tail to be, in this case, since it's a greater than, that rejection area to be 0.05. So if you fall in that area, if you fall in that shaded region, you're going to reject. If you don't fall in that 0.05, if you have a larger shaded region, you're going to fail to reject. So what conclusion can we make in this case at the alpha level of 0.01? So hold on a second. What happens here? Well, we have a shaded area of 0.0276. That's the p-value that we found. Our rejection level is way out here, and it says we only want to reject if it's less than 0.01. Well, do you notice how my shaded region there goes beyond the rejection region? I saw a larger probability than what I really wanted to see. And so my shaded region falls in this fail to reject region. So in this case, what would happen? Well, in this case, my p-value is greater than my alpha level 0.05. So what that means is the sample result is not statistically significant at that 5% level. Well, this should really be, this should really be a 1% and a 1% here. So we do not have enough evidence to reject the null. And I don't want to say that I'm wrong, so I'm going to say we cannot conclude The deluxe AAA batteries made by this company last longer than 30 hours on average. So, think of it like shaded regions. If your p-value is completely inside that shaded region, reject a null. If your p-value starts to go towards the middle, that shows a probability of it happening, and not rare. It shows likelihood. So you fail to reject the null. And when you fail to reject the null, you do not have enough evidence to reject the null. So we fail to reject, so we cannot conclude our alternative. There is a big distinction between measuring the strength of evidence and making a decision. So keep that in mind when it comes to your p-value for it. And again, think about the shaded region. Your p-value represents the area in either the tails or both tails based off of what type of test you're dealing with. So if I have a larger p-value, there's a very good chance I'm crossing into the fail to reject region. If I have a smaller p-value, what happens is I could be in that tail where I'm going to reject. And I keep saying the word p-value because that's the terminology you're going to use, but think of it like the area under the normal distribution curve. If the area is less than your alpha, then you're falling in the rejection area. If your area is greater than your alpha, you're starting to come towards the middle of the distribution, which means it's more likely to have occurred. So one thing about inference as a decision, the transition from measuring the strength of evidence to making a decision is not a small step. And that's something we're going through in the previous slides, is the strength of the evidence to making a decision is not a small step. I'm measuring that. We have to learn the p-value. So I want you to think about it like normal distribution, area under a curve, and alpha levels are those tails that you're looking at. And you need to start thinking, does your p-value start to come outside that alpha level, or does it stay inside that tails? The rejection versus failed rejection zone in the pictures I showed you. So many people believe the decision should be left to the user and not the statistical tests. So a test result is only one among many factors that influence a decision. And you want proof? Let's look at Dumb and Dumber.
What do you think the chances are of a guy like you and a girl like me ending up together?
Well, Lloyd, that's difficult to say, and we really don't...
Hit me with it. Just give it to me straight. I came a long way just to see you married. Just, least you can do is level with me. What are my chances?
Not good.
You mean not good like 1 out of 100?
I'd say more like 1 out of 1,000,000.
So before I keep going on with the video clip, think about this. He says, what are my chances? And she says 1 in 1,000,000. And so here's the distribution of how does Lloyd's alpha value compare with Mary's p-value. So the probability value given by Mary to Lloyd is 1 in 1,000,000, 0.000001. Now, what is Lloyd's alpha level? And so I want you to keep this in mind. So here we have this. Is Lloyd decided, and we're going to do hypotheses tests. And so Lloyd, the null hypothesis is that the love that Lloyd has for Mary is the same. Now, the alternative hypothesis is that Lloyd's love is greater than Mary's love. And really that also means Mary's love is less than that Lloyd has. Mary doesn't love Lloyd as much as Lloyd loves her, in other words. So which of these represent, if this is what's going on, and she says you have a 1 in 1,000,000 chance, which alpha level do you think Lloyd wants? Does he want this alpha level 1? Does he want to set his alpha level here? Or does he want alpha level 2 here? Because Lloyd really loves Mary and he wants Mary to love him. So which level do you think he would set it at?
So you're telling me there's a chance? Yeah!
All right, so here's what he did. He decided that, 1 in a million, so he said there's still a chance. So in other words, he told Mary that, hey, you failed to reject me. And so he set his alpha level right here. He set his alpha level to be that alpha level 2. Which means he was making his alpha level so small, she failed to reject him. Mary probably wanted the alpha level to be at alpha level 1, where she said, hey, it's about 1 in a million, so you're way over here and you're so not in my league. So the rejection level, Lloyd could have set it so tiny that her 1 in a million was bigger than what he set it for. I know, it doesn't really matter, but it's actually pretty funny when it comes to it. So, why choose a significance level? It gives a clear statement of the strength of evidence against the null hypothesis. The p-value does this for us. Now, if people think the null is true, then convincing evidence, strong evidence, is needed to persuade them, a small p-value. So keep in mind the consequences of rejecting the null hypothesis in favor of the alternative. Changes will need to be made if strong evidence is convincing against the null hypothesis, and changes cost money. These are little things not too important right now, but we start to get into these as we go through. So the main idea that we need to get into when it comes to this whole thing could be on your chart. It is p-values are going to be areas under the curve, and you need to have a smaller area, a less area than what you set with your rejection level, which is your alpha. So the red region is your alpha level, 0.05, 0.01. That blue part I sketched in is the p-value. If the whole sketch is inside the rejection level, which means less than your alpha, then you're going to reject. If the p-value becomes bigger than the rejection level, your alpha level, you're going to fail to reject. You also want to make sure you know how to interpret a p-value in context. Look at that in the book. That's something you should really understand as too. So, you have the p-value with the alpha level, the reject, fail to reject with the normal distribution curve, the shaded regions I just showed. You have interpreting the p-value in context. The third thing could be the conclusions that you have, and the whole statement is, don't accept the null hypothesis. You either reject the null or you fail to reject the null. If you reject the null, you conclude the alternative. If you fail to reject the null, you cannot conclude the alternative. But don't accept the null. Lastly, if the p-value is less than your alpha, remember alpha is the rejection level. That area under the curve that if you fall in that less than area, smaller than the alpha level, you're going to reject. And if that happens, the data that we find is statistically significant at that level, which does not mean important. It means that what we saw was not likely to have occurred by chance. So that's why when it falls in that area, we can reject the null and conclude the alternative. So as I said in the beginning, yes, it's section 9.1, the basics, but there's so much foundation here with significance tests when it comes to terminology, phrasing, and conclusions that you need to make sure that you actually read the book on this one and you understand what's being said.